This is video 11 using VL53L0X devices for distance ranging on STM32 MicroPython and the BlackPill. The code for this video is at the GitHub site. The information presented in these videos on MicroPython should work as well on any STM32F4 board. All code examples have pin definitions at the beginning of the file to allow the programmer to alter as needed. As this channel covers multiple microcontroller solutions over time, please subscribe to stay informed and click like, as that really helps. In this video, we use our STM32 BlackPill microcontroller on the STM32F411 baseboard with an external VL53L0X board to perform short distance ranging. A VL53L0X is a sensor device with a tiny invisible laser that can measure distance to an object. Ultimately, we learned how to get accurate readings, but it required a lot of testing of settings and readings of the data sheet. Hopefully you will find the whole process interesting. Let's begin with the sensors. The technology is vertical cavity surface emitting laser and can be used in light detection and ranging LiDAR systems. I purchased 10 devices for $15 from AliExpress. To get readings, you simply connect using I2C. Besides the I2C pins, there's also a pin called XSHUT and a pin called GPIO1. From the datasheet available in the GitHub site, it explains that XSHUT is a digital input pin, active low, and that GPIO1 is a digital output pin that is an interrupt output. It is an open drain output. So I left these unconnected. I began testing by using the surface of a cardboard box for my test target. I used this object as it was a large target for the sensors, but easily positioned on my cutting mat with the large printed metric ruler. The sensor uses standard I2C communication, so we can easily connect the device to the BlackPill I2C header pins. As I wanted to connect 3 VL53L0X boards, I decided to use MicroPython's soft I2C feature, which means the setup can use any 2 pins. Given that the device board is only $1.50, I felt this board had promise for use in future projects that gather distance data. First though, I wanted to see if I could get accurate readings. To this end, I developed 2 test approaches. First, I knew there might be bad devices, so I gathered several sensor boards and soldered the header pins to use on a breadboard. In this manner, I could collect data from several sensors. I placed 4 devices on a breadboard and wired to the BlackPill's I2C pin. I ran my I2C scan program, which gave me a hex 0x29 value, and that indicated the setup was wired correctly. Using the cutting mat ruler as a guide, I chose a target point 350 millimeters from the sensor to place the cardboard box. Additionally, I would do a second test to get readings at different distances. So I was ready. Test 1 is simple. Verify the I2C address, point the device to a flat surface 350 millimeters away, and collect 9 samples for each device. I used the driver and test file provided at Kevin McAleer's GitHub site. It was written for MicroPython on WP, so it was easy to substitute the I2C pin names for those on the BlackPill. Otherwise, I installed his driver file to the BlackPill and used his test program unmodified in Thony. The testing collected a lot of data, and I placed the output files as spreadsheets in the GitHub site. Here is a brief view of the data. As you can see, none of the devices measure exactly 350 millimeters. Bear with me. We will get to better readings ultimately. Viewing the data on a graph is helpful because we can see that 2 devices are just a bit high and 2 devices straddle the 350 millimeter target. By the way, each time the device operated, the very first reading returned 8141. So I learned to just remove that value from any output. Meanwhile, although I did not get a reading of 350 from the devices Each device was consistent to itself. Time for test 2. In test 2, I connected 3 devices on the breadboard and modified a copy of the test program to perform 3 readings. I took readings at different target distances. In the left-hand table, you see an example of the data I collected at 350 millimeters. You can see the data in the GitHub site. Here, I summarize the data in the right-hand table. I saw the readings deviate the most whenever the target was very close, like less than 5 centimeters away. The readings varied more as the target got very close to the emitter. To understand this better, I decided to determine the accuracy. To do this, I calculated the error. The formula is straightforward. It's the expected value minus the actual value, divided by the actual value. To get the percent, the value is multiplied by 100. In the table, target is the expected value, and the device readings average I used for the actual value. When I graphed it, I got a bowl shape with the lowest error occurring when the target is between 300 and 430 millimeters distance. However, I was still bothered by the reading values. Why weren't they giving me accurate readings? So I went back to the datasheet. It described different profiles and suggested accuracy is impacted by lighting conditions, indoor versus outdoor, etc., and program setting changes. Perhaps there is a better accuracy with a white target versus a gray target, I thought. So I decided to do a third round of testing that used different target colors and setting changes. I began with a cardboard box as the target. Now I added a large white foam as a second target and a black leather case as a third target. I did a quick test with the target being 350 millimeters away, and I added a minor 100 millisecond delay between the pings. The readings for the white foam averaged 350.5 millimeters. Wow! This meant the devices were viable. Next, I wondered if any of the program driver settings might impact readings, as suggested by the datasheet. I ran more tests at 400 millimeters because that seemed the optimum distance based on my earlier test. This table has a representation of a sample run and the settings of the test. As you can see, I changed the budget timing, pulse periods, and ping delay. The biggest impact was, of course, the target's surface color. The setting changes I made earlier did not improve the readings. I believe the driver author already had optimized the settings. Based on this knowledge, I felt I knew how to use the device. In summary, the sensor is fast and affordable. It's good to have several devices for a project and to pick the ones that report accurately. A key factor is the target's color and to operate them for distance ranging in the optimal range. Now that I understood the device better, I felt this sensor could have a place in future projects. Hopefully you too now have a better understanding of the TOF-VL53L0X board using MicroPython on an STM32 microcontroller. In the next video, we will look at other time-of-flight sensors and see if they are better. Thank you.